Hello class, and thank you for watching. In the second part of topic 1.5, polynomial functions and complex numbers, we're going to identify key characteristics of a polynomial function related to zeros when suitable factorization is available, or we'll use technology. In today's lesson, we're going to focus on specifically solving inequalities, polynomial inequalities. Now, remember that the notation f of x means that we're looking for the y values of the graph of f of x. So if we are asked to find out where is f of x greater than 0, that means that we're looking for the y values that are greater than 0. And this applies in terms of the graph, where the graph of f of x is going to be above the x-axis. And if f of x is less than 0, that means that the y values are going to be negative, and that occurs when the graph of f of x is below the x-axis. So let's look at an example of this. For example number 1, consider the graph of f of x. So here we have a function, this is f of x, and we want to and the question is, where does this function, where does f of x equal to 0? Well, in order for the graph to equal to 0, that occurs again when we actually cross the x-axis, okay? Any function equaling to 0 is simply where the location of our x-intercepts occur. And for this example right here, that occurs at this coordinate for here. Let me do it in blue. And at this coordinate and at that coordinate. So where does f of x equal to 0? Well, that occurs where your x value is -1, your x value is +2, and your x value is +3. Now for part B, where is f of x greater than 0? Well, that means again that the graph, we're looking for where the graph is going to be above 0. And the graph is above 0. Let me highlight it in green. Here in this green section. These are all of the y values where this is all the y values that are going to be greater than 0. They're going to be positive numbers, okay? So where is this graph greater than 0? Well, that occurs again right here, from here to there. And since we're looking again for the intervals, again, for the x value, that's going to occur from the x value of -1 to the x value of 2. Notice that this graph, again, that I just highlighted in green, again, is above the x-axis from this point to that point, where the x value is, like I said, -1, and the x value is 2. So we're above the x-axis from here to here, from 1 and 2, which in interval notation is written like this. So this is where we are above the x-axis. This is where the function is going to be greater than 0. Well, that is not the only place where our function is greater than 0. Our function is also greater than 0 in this portion right here. This part that I've highlighted in green is also above the x-axis. Well, for what x value is that? Well, it starts to be above the x-axis at +3. So we're going from 3 all the way to infinity. And not positive infinity because the graph is going up, because positive infinity because we're moving to the right of that location. So you see here and over here is where we find that the graph is above the x-axis, so 3 to infinity, which in interval notation is 3 to infinity. So this is the solution to this question. Where can we find that f of x is greater than 0? It's finding the intervals where a function is going to be above the x-axis. The third question is asking where is our function less than or equal to the value of 0? Well, we know that we equal to the value of 0 at these locations, at -1, at +2, and at 3. But this part is asking, okay, where is it also going to be, and the word and, equal to or less than 0, not and, but greater than or equal to 0. So, less than or equal to 0. So to find where the function is less than or equal to 0, like I said, we know that it equals to 0 at these locations. But where is it going to be less than 0? Well, it's going to be less than 0 and I'll do it in purple. And again, this is less than 0, this purple section. Well, where do we see that the graph is less than 0? Well, to the left of this point, of that point right there, we see that to the left of this point of -1, this portion of the graph is below the x-axis. So here, it would be all of the x's to the left of -1, which is from -infinity, if I read this from left to right, from -infinity to -1. And again, it's not -infinity because the graph is going down. It's -infinity because I'm looking at the left of the number line of my x-axis. Again, I'm focusing on the x values. Again, on the x values. What are the x values that will make the y values be negative? Well, those are going to be the x values that are to the left of this -1. So my answer is from -infinity to -1. So -infinity to -1. Now there is a distinction and something different on this one. On the previous example, we were looking for the numbers, the x numbers that were going to exclusively make the y values be positive, not equal to 0, just be positive. So we said the intervals, open intervals, because we did not include the endpoints. Because if I included the endpoints, that's where x equals to those values. So I cannot include these endpoints. But on this example, since I'm looking for the values where the y value is going to be less than 0, that happens at the x values from -infinity to -1. But because of the equal sign, that means we also have to look at what makes this equal to 0. Well, we equal to 0 at -1, as we said right there. So to include that and to say that not only are we figuring out the values where y is going to be negative, but also equal to 0, we use again a bracket to indicate again that we have and are including that endpoint. So if we do not want it to equal to 0, we use parentheses to indicate that we're not going to use the endpoints. We do not include the endpoints where the graph is greater than 0. But if we're going to have it equal to 0, then we use a bracket to indicate that. So for example, on this one, if my question was instead, where is f of x greater than or equal to 0, then we would include the endpoints, because between -1 and 2, the y values are going to be positive. They're going to be greater than 0. But at -1 and at +2, it's going to also equal to 0. So to indicate that's going to be all the numbers in between and equal to 0, we use brackets to indicate again that the endpoints are going to count. So the other one would be 3 to infinity. On infinity, we do not use brackets ever, because again, infinity is not an actual number, it's just a concept that we're going to get close to a very, very huge number. And because it's not an actual value, we always use open parentheses or the open interval, the normal parentheses on that endpoint there. And the same thing is going to be true on letter C. So instead, had the question asked this instead, where is f of x strictly less than 0, that would just simply change the interval from being a closed interval on the -1 to being open on that endpoint of -1. So that's what that would change. Let's see, now let's look at the next page. Now, for solving nonlinear inequalities, again with polynomials, what we begin by first is just first solving where the equation is equal to 0. After figuring out again all the places where it's equal to 0, we're going to create a sign chart with the solutions from step 1. We then test values at each interval to see if the values in the interval are going to be positive or negative. Positive means that the graph is going to be above the x-axis, and negative means that the graph is going to be below the x-axis. We interpret the sign to answer the given inequalities from the problem. And again, note, make sure to write your interval notation and think about the endpoints. Think of what it is that we're looking for, okay? So right here, to solve this inequality, where is x minus 3, x plus 1, and x plus 4 going to be greater than 0? Well, to figure this out, we first have to figure out where is x minus 3, x plus 1, x plus 4 gonna actually equal to 0. Well, this is going to equal to the opposite. Since this is already in factor form, that's going to equal to the opposite of each linear factor. To make x minus 3 equal 0, that means that x would have to be positive 3. To make x plus 1 equal to 0, that means x would have to equal to negative 1. And in order to make x plus 4 equal to 0, then x would have to equal to negative 4. Okay, so we found where the values of x that will equal to 0. So what we're going to do now is that we're going to use a number line and to see what's happening to the left, to the right, and in between these intervals. Now, since we're going from negative infinity to positive infinity, we have to make sure that our numbers are written in the order from least to greatest. So negative 4 is smaller than negative 1, and negative 1 is smaller than 3. So from least to greatest, this is what the number line will look like. Now, it doesn't have to be drawn to scale. Again, the idea is just to simply draw a generic number line, and it does not necessarily have to be drawn to scale like the one I have here. Okay, now to figure out where is this graph going to be strictly greater than 0, we're going to, again, to be greater, that means it has to be above up here, okay, above those values. So that means, again, that the y values have to be either positive or negative. Positive means they will be greater than 0. Negative means that they are less than 0. So to figure this out, we're going to just simply test values that fall within this domain of negative infinity to negative 1. So I'll pick any number that falls within that boundary. We'll pick negative 10, for example. So I'm going to have x equal to negative 10. So I'm going to substitute in these x's with that number there. So negative 10 minus 3, negative 10 plus 1, and negative 10 plus 4. This is going to be negative 13, negative 9, and negative 6. Now I'm really interested again in figuring out what type of sign I'm going to get, not what the actual number is, okay? All I care about is the sign. So multiplying a negative and a negative, that's going to be a positive value. And then multiplying that positive value with another negative, that's going to end up equaling to a negative value. So multiplying 3 negative signs together, that's going to result in a negative number. So I know that from negative infinity to negative 4, we're going to end up with a negative value. That means that the graph of this function, whatever this function is, f of x, h of x, whatever, this portion of the graph is going to be below the x-axis. So the graph is going to go upwards and below, and is going to equal to 0 at that location. Now, to figure out whether the graph is above or below the interval of negative 4 to negative 1, we're going to do the same thing, but this time use a number that falls within that boundary. So between negative 4 and negative 1 is the number negative 2, for example. We could pick negative 3, or we could pick negative 2.5, any number, but I'm going to pick negative 2. So let's see what's happening there. So I'm now going to have x equal to negative 2. So I'm going to just do the same thing. Negative 2 minus 3, negative 2 plus 1, and negative 2 plus 4. We end up with negative 5, negative 1, and positive 2. And again, I'm only interested in figuring out, again, this is going to end up being less than 0. And I'm only interested in figuring out if I'm going to end up with a positive or negative number here, okay? So multiplying a negative and a negative, well, that's going to be a positive value. And multiplying that positive value with this positive 2, that's going to result in a positive sign. So that means that this portion of the graph is above the x-axis. And again, I just continue testing. And now to figure out if the graph is above or below in this next portion, in this next interval, sorry, I didn't mean to erase that. In this next interval, again, I just simply pick a number that falls within that interval. between -1 and 3 is the number 0. So let me use 0. 0 is an easy one to use. So if I pick 0, this would be 0 minus 3, 0 plus 1, and 0 plus 4, which is -3, +1, and +4. Well, multiplying a negative with a positive, that's negative, and multiplying a negative with this +4, that's going to result in a negative number. So that means since this is negative, that means that this portion of the graph is below the x-axis. And finally, for the last one, so I'm going to pick any number that's greater than 3. I'm going to pick the number 5. Okay, 5, and I'm now going to plug in that value of 5. I'm out of space here, so I'm going to just make this smaller. So if I plug in 5 into the x's, so in the first parentheses, that'll be 5 minus 3, 5 plus 1, and 5 plus 4, which is a +2, 6, and 9. And obviously multiplying positive numbers with positive numbers, that's going to be a positive value. So this portion of the graph is going to be above the x-axis. So there. Now having figured out again what's happening on each part of the interval, where's the function, where is this? Let me highlight. Where is x minus 3, x plus 1, x plus 4 going to be greater than 0? Well, to be greater than 0, again, positive numbers are greater than 0. So we are going to be greater than 0 between -4 to -1, and then from 3 all the way to infinity. So the solution to this is -4 to -1 and 3 to infinity. So any number that falls within that interval is going to be greater than 0. Now, since we don't want it to equal to 0, we exclude the endpoints and we don't count the endpoints, and we do not use brackets. The difference between having an equal sign, like I mentioned in the first page, is that had this had an equal sign, then that just simply would mean that we would have brackets on the endpoints, with the exception of infinity. Infinity, we never put brackets around infinity. So let's look at a second example. So for this example right here, the same idea, we want to figure out where is this function going to be less than 0. So we want to solve this inequality. So we start by first figuring out what's going to make each linear factor, x plus 2 to the second power and x minus 5 to the first power, equal to 0. Well, to make the first parentheses equal to 0, that means it's going to be -2. Remember, this number doesn't affect what's going to make what's in the parentheses equal to 0. This just tells us that x is going to equal to -2 a total of 2 times. And x is going to equal to +5 in order to make this parentheses equal to 0, 5 minus 5. So here are the two zeros. This is where the graph is crossing or intersecting the x-axis. Now, recall that since this factor is raised to the second power, an even number, that means that this one right here, this one's special, we're going to be tangent at this location, okay? And I'll explain how that's going to be special to make our work easier to do. And we can see again what's going to happen to the left and to the right of -2. So we're going to make our number line from negative to positive infinity and break this up into two sections, from -infinity to -2 and from 5 to infinity. And not to sound like a broken record, but again, I put them in this order because again, that's in the order of our number line from least to greatest. And now what I'm going to do is I am now going to pick numbers that fall within this boundary region right there, okay? Now, x plus 2 to the second power, remember, means x plus 2 times x plus 2. And then we have an x minus 5. So we're going to start by picking a number that falls within negative infinity to negative 2, like negative 10. So negative 10 plus 2 times negative 10 plus 2 times negative 10 minus 5. Well, negative 10 plus 2, that's going to be a negative number, negative 8 specifically. Negative 10 plus 2 again is negative 8. And negative 10 minus 5, that's negative 15. Again, getting the actual values is not important. What's really important again is knowing that you're going to get negative values. So negative 10 plus 2, that's going to be more negative than positive, so that's going to be negative. So that's going to be negative, negative again, and a negative 10 minus 5, that's going to make it more negative, so negative as well. And multiplying 3 negatives is going to result in a negative value. A negative times a negative is positive, so these two become positive, and that positive number multiplied with that one more negative is going to become negative. So in this portion of the graph, we have that the y value is going to be a negative value. Okay, so that means that the graph would be less than 0 in that coordinate. Now we have to pick a number between negative 2 and 5, which the number 0's in there. So 0 plus 2, 0 plus 2, and 0 minus 5. So 0 plus 2 and 0 plus 2 is positive 2 and positive 2 respectively, and 0 minus 5 is negative. Well, right here again, obviously 2 positives is a positive, and a positive times that positive answer times this negative number is going to result in a negative value. Again, knowing what the actual number is isn't that important. But because it's negative, that means that this right here is also going to be negative, less than 0. And then our third interval. Well, from 5 to infinity, the number 10 is there. And again, you can use the number 6. Doesn't really matter. As long as you pick a number that's greater than 5. So, but I'm going to use 10. I like using 10. So 10 plus 2, 10 plus 2, and 10 minus 5. Well, 10 plus 2 is positive, 10 plus 2 is still positive, and 10 minus 5, even though we're subtracting, we're still positive because we have more positives than we have negatives. And multiplying 3 positive numbers together is positive. The answer would be a positive number. Okay? So where is this function less than or equal to 0? Okay, well, the equal part, this part right here, the equal part, this part right here, that occurs again at negative 2 and 5. Okay, but we also want it to be less than 0. Well, less than means it's going to be negative, so it's negative again in those regions from negative infinity to negative 2, okay? And because we also want it to equal to 0, right? Equal to 0, that's going to be a closed bracket. And it's also less than 0 from 2 to 5, again, where it's negative. So from 2 to 5, right here it's also. So negative 2 to 5. Okay, and close bracket as well, because again we're going to include the endpoints because we also want it to equal to 0. So since we also want it to equal to 0, that means we're going to include the endpoint, so use brackets. Now in this particular situation, notice that I have a bracket on 2 on the left end of 2 and on the right end of 2. In those circumstances where I stop and I end again in the exact same location, and I'm including that endpoint, then I can simplify this interval, and by simply stating that we're going to go from negative infinity to negative 2, including the negative 2, and then continue from negative 2 to positive 5, still including the negative 2, then that's just simply the same thing as stating that our interval will go from negative infinity all the way to 5, from start to end. But that only works if these two things here are both brackets. If we were not making it be equal to 0 and these were parentheses, then we cannot make this into one interval and say we're going to go from start to finish here to here if these numbers, even if these numbers are the same. The only way we can simplify it to 1 is that these things have to be brackets. So this right here would be the simplified form of this statement. While both of these statements are the correct, on a multiple choice test, this would be the correct format of seeing it. And on an open response question, you would have to write like this in order to get full credit. Okay, so this is going to be your answer. Now, before we move on to the next example, let's talk about again, look what happens right here from negative to positive 2. Notice that we end up again with two negative signs. It didn't alternate like the previous one, where it alternated from negative to positive, negative to positive. And the reason for that is because of this multiplicity. Recall that this point here, which I want to highlight in blue, we were tangent at this location, meaning that the graph is simply going to touch this point and then bounce off. So since on the left part of the graph we were negative, we were below the x-axis, we were getting to this 0, because we're tangent at that location, the graph is going to continue staying below the x-axis. So it's going to move down before it turns around and touches this next x-intercept. So since the graph started below the x-axis and we're tangent at this 0, it's going to stay below the x-axis before it gets to the 0 of 5. At 5, that's when it's actually going to cross the y-axis, the x-axis, and move above the graph. So we can see that we're going to be below the x-axis at those two locations. At this long interval, at this interval and this interval, which can be just simply be written like this. Let's see. Let's look at this next example. So moving on. On this example, in order to solve this inequality, the first thing we need to do is move everything to the right side. We need this side again to be the number 0. So we're going to start by moving these two terms to the left side, not right side, I'm sorry, to the left side. We want the right side to be 0. So this would be x to the third power plus 4x squared minus 10x to the second power plus 9x. You'll notice that we have two like terms here, and now this would be less than 0. And since we have these two like terms, this would be x to the third power minus 6x to the second power plus 9x. And now we can figure out where is this polynomial going to be strictly less than 0. So let's look. Okay, so we're going to factor this. Notice that there's a common factor of x. There's an x on every single term. So we'll start by factoring out that x. So x to the third power is now x to the second. 6x to the second is now negative 6x. And positive 9x is now going to simply be positive 9. Now we still can't figure out what's going to make this equal to 0, because remember, I need the linear factors. I do not have all of the linear factors because this is raised to the second power. So I need to break this apart to its linear factors. So the factors negative times positive is negative. So the factors of 9, those are 1 and 9, 3 and 3. And since these signs are the same, I want to add these up and match up to 6. Well, that's 3 plus 3 is 6. So this would be 3 and 3. And there you have it. Now that I have linear factors, x to the first power, x to the first power, and x to the first power, I can now figure out what's going to make each one of these things equal to 0. Well, for the first one, x will have to equal to 0. And for the second two, x would have to be positive 3. In order to make this equal to 0, x would have to be positive 3, and the same thing here. Okay? So for this one right here, because we have 2, our multiplicity is 2, we have 2 factors of x minus 3. So x is equal to 3 has a multiplicity of 2, meaning that x equals to 3 of total of 2 times. We are going to be tangent at this location, okay? So that would mean that to the left of 3 and to the right of 3, whatever the sign is on the left, on the right of that number 3 is going to be the same, just like over here on the top one. Since we were tangent at 2, and on the left side of 2 was negative, that means on the right side of 2 would also have to be negative. So let's create our little number line. So here is our number line from negative infinity to positive infinity. We're going to put the number 0 first, and then the number 3. And we're going to plug in numbers again into the factor form. We could plug it into this one up here. All right, we could plug it into this one, but the factor form is easier to work with because all we want to figure out is see what type of number we're going to have. So let's start by plugging in a number that is less than 0. So we'll do something simple. We'll do negative 10 yet again, okay? So right here, negative 10. So we're going to plug in negative 10 in for x. So negative 10. So negative 10. Negative 10 minus 3, and negative 10 minus 3 again. Well, this would be negative. Negative 10 minus 3 is negative, and negative 10 minus 3 is negative. So multiplying 3 negative numbers is going to result in a negative value. So between negative infinity and 0, we're going to be negative. Oh, let me highlight this, okay? Remember, right here, we are tangent. The graph's going to be tangent at 3. So let's pick a number now in between 0 and 3, like the number 1. So positive 1, that's this one right here, and then it's 1 minus 3 and 1 minus 3. Well, this would be a positive. 1 minus 3 is negative, and 1 minus 3 is negative. Multiplying, excuse me, I don't know what happened there, okay. Multiplying 2 negative numbers, that makes it into a positive. And multiplying that positive with the first positive, that makes everything positive. So we're going to be positive right there, okay. Now, because we are tangent at 3, that means that on the left side of 3 being positive means that the right side of 3 would also have to be positive. And again, because we're tangent. Just to verify, let's double check and prove that I am correct. So now, so to verify and prove that I'm correct, I'm going to pick a number that is greater than 3. So again, I'll pick 10. So for x, we're going to replace that with positive 10. In the second parentheses, that would be 10 minus 3, and x minus 3, 10 minus 3. Well, obviously 10 is a positive number. 10 minus 3 is also a positive number. And 10 minus 3 again is another positive number. And multiplying 3 positive numbers is positive. So you see, I ended up with a positive sign yet again. So using the fact, and that's why we were talking about graphs being tangent the other day, okay? Graphs being tangent and identifying where a graph is tangent helps us out in identifying where the behavior of our function to the left and to the right of points that the graph is going to be tangent to. So our graph is going to be tangent to x is equal to 3. So since the left was above positive, that means that the right is also going to be above positive. Okay. So now let's figure out the solution to this, all right? Now that we have this, we're trying to solve again this inequality. When is this function, this right here, which again we got from up here, going to be less than 0, negative 0. Well, that's going to occur right here from negative infinity to negative 2, 0. Okay? This is our answer. Now, let me propose a different situation. What if the question asked us this? Instead of being less than 0, what if it asked, when is x times x minus 3 going to be strictly greater than 0? Okay? Greater than 0 means that our y values would have to be positive. Well, we're positive here to here. So from 0 to 3, and from 3 to infinity. We're positive from 3 to infinity. This would be the solution to this one. And for this particular one, we will not be able to write a shorthand. Oops, I forgot the infinity symbol right here. There we go. We would not be able to compress this and write a simplified version of this, because right here, it's strictly greater than 0 and not equal to 0. Because it's not equal to 0, that means that the endpoints are not going to be included. Like I didn't include the 0 and I used the bracket. I only used my open parentheses because it's going to only be less than 0. And the same as right here. Since I'm only looking for exclusive y values that are greater than 0, that only occurs again for the x values that are between 0 and 3, not including 0 and 3. At 0 and 3, that's where the graph equals 0. Okay? Sorry, these should be equal sign. Well, no, they should be the same. Okay? This is where the graph equals to 0. So on this example right here, because these are not including the endpoints, we cannot write this. This is not the same. This is not the same as saying we're going to go from 0 all the way to infinity, okay? Because we are not including the endpoints. The only way we can compress it and write it as one smaller interval is if the following two things are satisfied. First is that we're using brackets on the two endpoints, and that the two endpoints, again, the endpoint and the new starting point, are the exact same number. So here, even though those numbers are the same, we end and start at the same number, we're not including them. So we cannot write this as one simplified, one compressed interval. Okay, let's change gears now. And let's talk about polynomials, but not inequality polynomials nor solving inequality polynomials, but how do we determine the degree of a polynomial given a table? Well, if we're given a table of values with equal width input values, and that's the key part, okay? Equal with input values, it can be determined that the degree of a polynomial by examining successive differences in the output value, which basically means if I see what the difference is for this, okay, the number of successive differences needed for the difference to be constant is equal to the degree of the polynomial. So what this basically says is that as long as these are consistent, they're increasing or decreasing by the same number, which this example is. This one is increasing by 2. My input value is increasing by the same number by 2. I can figure out the degree of this polynomial by determining how many times it takes for this difference right here to be the same. So for example, if all of these numbers, if the difference from here to here are all the same, then that means that this would be a polynomial of degree 1, because it only took one successive difference for it to be constant. If it doesn't, then it would be a degree 2 if it takes 2 times, degree 3 if it takes 3 times, and so on. So let's look at this example, example A. So to figure out the difference from -2 to 3, we're going to just simply subtract in the opposite order of my arrows. Negative 3 minus 2, that's a difference of plus 1. To figure out the difference from negative 3 to negative 1, I simply subtract in the opposite order of my arrow. Negative 1 minus negative 3, that's a difference of plus 2. To figure out the difference from negative 1 to 4, I'm going to subtract, again, 4 minus negative 1, which is plus 5. And here the same thing. To get the difference from 4 to 12, I'm going to subtract in the opposite order of my arrows. So 12 minus 4, which is 8. Since these numbers were not the same, this is not a degree 1 polynomial, right? So the degree of this polynomial is not 1. So I'm going to do it again. I'm now going to figure out the difference from 1 to 2. Well, that's obviously just plus 1. The difference from 1 to 5, that's plus 3. And the difference from 1 to... Oh, sorry, hold on, I made a mistake. Check that. That's negative 1. Negative 3 minus negative 2, that's a difference of negative 1. I got my signs wrong. Negative 1. Which would make the difference from negative 1 to 2 plus 2. So from negative 1 to 2, that's a difference of plus 2. To figure out what this number is, again, just simply subtract in the opposite order of my arrow. So negative 2 minus negative 1, I'm sorry, positive 2. Positive 2 minus negative 1, that equals to 3. And then from 5 to 8, that's also a difference of plus 3. So look, since it took 2 times to find where this number was constant, the same, that determines the degree of our polynomial. So our degree here is equal to the value of 2. That's how you can use the table to determine the degree of a polynomial. But again, this only works if this is going to be consistent. So like right here, this is consistent. We're increasing by 3. Nine plus 3, 0 plus 3 is 3, 3 plus 3 is 6, 6 plus 3 is 9, 9 plus 3 is 12. Now for the right side. This would be plus 2. This is plus 10, plus 17, and plus 23. This is a difference of plus 8, plus 7, and plus 6. And this is a difference of minus 1 and minus 1. And there, it is now consistent. Since these are now consistent, both negative 1, it took us a total of 3 times, once, twice, 3 times to get this consistency. That means that the degree of this polynomial is 3. And from the fundamental theorem of algebra, that means that we have an x minus some constants, we'll call it C1, x minus some other constant, and x minus some other constants, okay? These numbers don't necessarily have to be different, okay? But because of this, we know that there's going to be, again, a total of 3 linear factors. And then up here, the same thing. Since this is the degree 2, that means that there has to be 2 linear factors. c minus a constant, and then x minus a constant, and then x minus another constant. And again, they could possibly be the same one, all right? They could be the same number, or they could be different numbers. They don't have to be unique. But we know that having a degree 2 simply means this, that we're going to have two factors that are being multiplied together. And degree 3 means that there has to be 3 factors that are being multiplied together, again, by the fundamental theorem of algebra. And let's check the last one, okay? So for the last one, again, this is consistent. This is increasing by 1. And let's see here. To figure out the difference right here, just simply subtract backwards from the order. So -7 minus -17, that's a total of 10, positive 10. So it increases by 10. This is going to increase by -13. -5 minus -6. Oh, no, this was negative. I did this one backwards, my bad. -6 minus -7. That's an increase of 1. -7 minus -17. Yes, that was 10. -5 minus -6. That's also going to be 1. And 2 minus -5. That's going to be 7. So this increases by 7. Let me move this out of the way. And now from here to here, that's 1 minus 10, which is -9. 1 minus 1, that's equal to 0. And 7 minus 1 is equal to 6. So this is a difference of +9. This is a difference of +6. And well, this is only a difference of +3. So not enough information to figure this one out. So as you can see, there was no consistency, and because we ended up with at the very end with only 2 numbers, we can't determine if the next change from here to wherever the next number is also going to change by 3. So for this example, there's no way to determine what the degree of the polynomial is. There has to be a consistent change in a consistent change for the output values after and right here in this situation within the number of times again that we could subtract. So as a result, we can't determine this, okay? And well, there you have it. So that concludes our notes on the second part of 1.5. If you have any questions, please send me a message through email or through Parent Square. And like always, I appreciate you watching, and I hope you have a great day. Goodbye.